Welcome to Ready to Derive. In this video, we explore the power of the first derivative to help us analyze a function and sketch its graph with remarkable detail. While it is true that we now have graphing calculators at our disposal, and you might wonder why it's even necessary to sketch graphs by hand, it's very hard to pinpoint exactly important features of a graph without a mathematical analysis of its corresponding function. Hopefully, you'll also gain an appreciation for the lengths that the mathematicians in the past had to go to in order to make advances in their field, all before the advent of technology. So, without further ado, let's get started.
So, as an introduction to considering shapes of curves, let's revisit graphing a parabola, which is a curve we should be very familiar with. So, here's a quadratic equation. We know its shape is a parabola. We know because the leading coefficient is positive that it will be an upright parabola. And so we have a feeling it's going to look like something like this. And for now, we just want to find the x-coordinate of the vertex, as the instructions say. So to do this, we have to recall a formula, x equals negative b over 2a, which is the formula for the x-coordinate of the vertex. It's also the axis of symmetry. And it's also a component of the quadratic formula that you might recognize. So if we just plug, let's see what is. So this is a, b is the coefficient here, and c is here. Negative b, so the opposite of negative 12, over 2 times 3 is 6. That comes out to be 2. So we find that that is located at x equals 2. And if we wanted the y-coordinate, we could plug 2 back into the original function, and it will come out to be 1. So that's, very interesting, useful, but where did this formula come from? And this is where calculus kicks in. So let's look at the general formula of a quadratic in standard form, and let's think, well, what have we learned so far in calculus? We've learned about derivatives. And if we think about what the derivative of the function is here, because that's our horizontal tangent line at the vertex, we know that the derivative must equal 0. So why don't we take this general formula and take the derivative? Using the power rule, we get 2ax plus b. And then let's set that equal to 0 to find out where that happens. 2ax equals negative b, and if we solve that, we get the formula that once upon a time we had to memorize and just trust was correct, and now we have just proved thanks to the derivative. So the question is, though, we had that formula for a vertex, but for the vertex of a parabola, but we never really had a formula for cubics or any other more sort of advanced functions. So, for example, how would we sketch something like this? Well, now that we have the derivative, we know that there's a lot that we can analyze about functions, and that's what we're going to do next. So in this slide, we're going to look at a more interesting curve and see how the first derivative can help us sketch curves that are way more complicated than a parabola. And let's just put an xy axis there, even though I'd like you to think of this as kind of like a mountain range. And we're going to put somebody on that mountain range and describe what they're doing. Are they going uphill, downhill? Do they feel like they're at the top of the world or in a chasm? It all matters. It all ties into the first derivative. And if we look at this, as we consider this person is actually walking, what direction are they walking? Downhill, uphill? Well, the convention is we consider where they're going as x moves from smaller to larger. So as your x value increases, where are you going? And this person is clearly ascending the hill. And they are ascending the hill all along here until they get to this point here. So we say that the function is increasing here. And for it to be increasing, what that really means is that we know that the derivative there looks as if the derivative is positive. And if we now, let's consider at the top here, so the person ascends to the very top, they kind of feel like they're at the top of the world. They're not really. This isn't the absolute maximum of this function, but we would say that f has a local max here. And how do we know? What's one way we know that? Oh, well, it looks like f prime would equal 0 there. We have a horizontal tangent line. Then the person starts descending the mountain. And if they're descending, then we know along here, let's use different color. So along here, he's decreasing, decreasing, decreasing. So we'd say f is decreasing, and that means that the slope f prime, the value of the slope, should be negative there. What happens when they get to the bottom here? Well, they're going to feel like they are at a pretty low point, and they have a lot to ascend after there. But so we would say that f has a local min here, but not because f prime equals 0 here, but because f prime is actually undefined. And then they hop over that little chasm and then start ascending. So ascending all the way. Now we would technically, this person, or this function is increasing the whole time along here. So f is increasing, which meaning f prime will technically is greater than 0, although if we come and look right here, looks like this at this point here, maybe the derivative is 0. It doesn't correspond to a local min or max, but it is sort of a resting point for that person before they begin the rest of the ascent. So you can see that just by for f prime could be positive, negative, 0, or undefined, and that gives us so much information in order to be able to sketch the graph of a function. So in the last slide, we kind of made a loose connection between the sign of f prime and whether a function is increasing or decreasing. And in this slide, we're going to formalize it mathematically. So let's have a look at an increasing function, and let's bring up the definition of increasing, which you might have learned in pre-calculus, but if not, here it is. A function f is said to be increasing on an interval I if given x1 is less than x2. So let's mark this into, let's make this left endpoint x1 and the right endpoint x2, so we have this inequality be true. Then that must imply, it must follow, if that is true, that f of x1, well, this is f of x1, which is clearly has to be less than f of x2. So it's kind of common sense, but that's the proper definition. Now, what we're going to do is we're going to make this connection to f prime using the mean value theorem. And this is kind of cool because usually we only use the mean value theorem to prove problems that are clearly meant to be mean value theorem problems. So it's not so, we don't often use it for more advanced things. So in this slide, we're going to see how it actually can be used to prove the loose connection we made in the last slide. So what does the MVT say? It says that if you take the average rate of change over the interval, remember, so that's the slope of this secant line. That's what this quantity here represents, the slope of the secant line. It says that that must be equal to the slope of the tangent line at some point C. So I'm going to see where that looks about parallel right there. So we're thinking C is around here. And what we have to think about is, well, we want to know, we're going to be given a function and we're going to take derivatives, and using the derivatives we'll be able to tell whether a function is increasing or decreasing. So we might say to ourselves, well, what if the derivative is, what if the derivative is positive? Does it follow that the function is increasing? Well, look at this. Remember, if x1 is less than x2, if that is true, then x2 minus x1 has to be a positive quantity. And if f prime c is positive, well, the only way that we can kind of complete this and make it true is if the numerator is positive. And what does that mean? If f of x2 minus f of x1 has to be positive, it must follow that this inequality holds true, and therefore it implies that the function is indeed increasing according to the definition. So very simple use of the mean value theorem to sort of prove this important result. If f prime is positive on an interval, then f is increasing on that interval. Similarly, if f prime is negative on an interval, then we could conclude that f is decreasing on that interval. So let's look at how f prime can inform us about the location of local, or otherwise known as relative, max or min. And let's bring up this interesting figure from before. So we know we identified a relative max right here, or local max. Sorry, I'll go back and forth between those two terms. They mean the same thing. So here we had f prime was 0, And we knew that we had kind of a local min here, and that f prime clearly is undefined. The function is not differentiable there. So these are very important points, and the way to find these points, because they're so important, they're actually given a name. So these are critical numbers or values of a function, and they're numbers c in the domain of the function such that either f prime of c equals 0. So let's have a look. Let's call this, if we call this c1, then we could say, well, we know that f prime of c1 equals 0, or f prime of c is undefined. So let's call this c2. Clearly, f prime of c2 does not exist, is undefined. And these critical numbers clearly give us candidates for possible local max and min. In fact, this is true. If f has a local max or min at c, then you can be guaranteed that that c is a critical number of f. So either of these two will be true. But what about the converse? If c is a critical number of f, then f may or may not have a local. Let's have a look at this. May or may not have a local max or min at c. Well, clearly for c1 and c2 is true, but let's have a look over here. Let's look right here. Call this c3. Clearly f prime of c3 equals 0. So c3 is a critical value, but it is neither a relative max or min. So now we need a way to determine, once we get the critical values of a function, whether they are local max, mins, or neithers. And this is where the first derivative test comes in. This is a very important result in calculus. It's kind of common sense, but it's helpful nonetheless. So suppose that you've actually obtained the critical values of f, and let c be a critical number of a continuous function. Well, what makes c a local max, min, or neither? It's really all about f prime again. So f prime will give us the critical values. That's how we get the critical values. And then f prime will help us analyze as to whether they're max, min, or neither. So let's look at this. If f prime changes from positive to negative at c, then f has a local max at c. So let's have a look at that. How could that happen? If f prime is positive, well, that's f prime positive to the left of c, and then f prime becomes negative to the right, so the function goes from increasing to decreasing, we know that f has a local max at c. In the same vein, if f prime changes from negative to positive at c, so f prime is negative on one side of c, let's call that c, and f prime is positive on the other, then we have a local minimum. So what happens if it doesn't change sign? Well, we have neither local max or min, and we either have this situation that we had in the previous slide, so this is c, and we see that to the left of c, f prime is positive, and to the right of c, it's also positive. The function is still increasing, so neither a local max nor min. And similarly in the other direction, so if that's c, we see that f prime is negative before c, and after c, it's still negative, does not change sign, and therefore there's no local max or min. So the first derivative test is absolutely instrumental in being able to analyze and graph a function. So let's put together all that we have learned about the first derivative and how it informs the analysis of a function. And let's revisit the cubic function from the first slide that we sort of wondered how we could sketch that if we don't have any formulas as we do for a quadratic. So let's get to work. So the first step obviously is to find the critical values of f of x, because it's the critical values that could possibly be max or mins, and it's also on either side of the critical values that the function changes from increasing to decreasing or vice versa. So the first step is to find the derivative, and if we do that, 3x squared minus 6x minus 9. And the critical values, remember, occur when f prime x equals 0 or f prime x is undefined. Clearly, there's no value of x for which the derivative is undefined, so we set this equal to 0 and solve. And factor out the 3, and we get this. And continue factoring, and we get that the critical values are x equals 3, and -1. And let's recall this is still f prime x, and having it in factored form is going to be very helpful for us. So let's keep it in factored form for now. And the next thing to do then, now that we have these critical values, we want to find the intervals on which f is increasing or decreasing. Now we know that f is increasing whenever f prime x is greater than 0. So you could say, well, why don't I just take f prime x and make it greater than 0 and solve that? But solving an inequality like that is challenging because there's two ways you could get a positive answer. You could make sure you have a positive times a positive, and that will be greater than 0, but also a negative times a negative, and that will be greater than 0. And there's a lot of moving parts here trying to solve this algebraically. So a much better choice is to use what's called number line analysis. So in the number line analysis, you plot on a number line, you plot the critical values, so -1 and 3. And then what you do is you consider the intervals that -1 and 3 create, and you kind of test values to see whether f prime is positive or negative. So I am going to I'm going to label this according to this, that is the derivative. So at -1, we know the derivative is 0, and at 3, we know the derivative is 0. So what we do is we take test values in respective intervals. So let's look for a test value in that interval. We could take -2, and we put -2 into the factored form, and then we think about the sign. So -2 minus 3 is -5, but it doesn't really matter. What I really want to know about is the sign. So it's negative there. And -2 plus 1 is also negative, and a negative times a negative is a positive. So we know that f prime x is positive in this region. And we proceed. So now we take a value in this region, and 0 is always a good one, and we plug in 0 and go through the same motions. 0 minus 3, that's negative, 0 plus 1 is positive, and multiplies together, and that will be negative. So we know between -1 and 3, that f prime will be negative, and we know it can't change because there's no other critical values between -1 and 3. So f prime has to be continually negative in that interval. And then we pick one more in the final interval. So we could use 4 minus 3, 4 plus 1. See how easy it is to plug it into the factored form rather than the unfactored form. So 4 minus 3 is positive, 4 plus 1 is positive, the overall effect is positive, and we get this. And then we can see that it tells us a lot, because if f prime is positive here, that means f is increasing, like this. And if f prime is negative here, that means f prime is decreasing, like this. And sorry, no, f is decreasing. And when f prime is positive again, we know that f is increasing. So let's summarize what we've discovered so far. So we found the critical values, x equals -1 and 3. We found that f is increasing on these intervals, and often you have to justify why. So you would say because f prime x is positive here, as we discovered in the previous slide. Notice that I'm using open intervals. Some textbooks and teachers will want you to use closed intervals, obviously not at -infinity, but at -1 and 3. So just be aware of that, depending on the kind of definition of increasing, decreasing, that may be necessary. And we also found that f is decreasing on that interval because f prime x is less than 0 here. So the next step to complete the picture of this function is to find any local max and minimum values. And we realize actually that that number line analysis from before actually contains the answer to this problem. So let's bring that up, recall that. And according to the first derivative test, we know that if f prime changes from positive to negative at a particular value of x, then we have a local maximum there. So x equals -1 must be a local maximum because f prime changes from positive to negative, which means f goes from increasing to decreasing. So we know that we have a local max at x equals -1, And if we look here, we see that we have a local min because f prime changes from negative to positive, which means that the function itself is going from decreasing to increasing. So let's now put all this analysis into creating a sketch of the function. And it's always good to start with the local max and mins first. So at -1, if you plug -1 into the function, you will get 9. So you can check that for yourself, confirm for yourself, but we have like a local max there. And at x equals 3, this is not drawn to scale, we have a local min. If you kind of sketch those local max and mins in first, then you can check that the increasing decreasing really works. It matches your max and min. So yes, this looks good. It is increasing, f is increasing up to -1. That's check. Decreasing from -1 to 3, check. Increasing from 3 to infinity, check. We're not so concerned with x-intercepts, etc., y-intercepts, but you could sort of figure those out if you had to. X-intercepts might be a little hard to find because it's a cubic function. But for our purposes, for calculus, we've just used the first derivative to accurately sketch the behavior of this function, the important features of the behavior of the function. So we'll end with one final example, analyze and sketch this rather unusual function, and we'll sort of not go into great length justifying conclusions and things. We'll just use a number line analysis to really get at the essence of graphing this function. So first of all, we have to find the critical values. So it would be wise to rewrite this as 12x to the 2/3, so we can use the power rule. And that would make f prime x. If we bring the 2/3 down and multiply by 12, we get 8. When we subtract 1 from the exponent, we would get to the -1/3, minus 4. And it's sort of convenient maybe just to rewrite that as 8 over the cube root of x minus 4, especially if we're going to sort of plug in values for x. Now, so what we've actually created here is a situation where f prime x is indeed undefined. So even though if you look at the original function, the domain is all real numbers, we have one value of x, that's a problem because it will be in the denominator. So f prime x is undefined when x equals 0. So that is one of our critical values. To find the other one, we have to set f prime x equal to 0. And when does that happen? Well, let's set it equal to 0. If we solve this, let's see, put the 4 to the other side. We rearrange this, we'll get cube root of x equals 2, which gives that x is actually equal to 8. And so our two critical values are 0 and 8. So next we'll dive straight into the number line analysis. And we start by plotting those critical values. And we are observing the behavior of f prime x. So here at 0, it's d and e. Here at 8, it's 0. So let's call up the derivative formula and let's pick some test values. So we'll pick a test value in this region, maybe -1. The cube root of -1 is indeed negative, so we have -8 minus 4, which comes out to be negative. Let's pick a test value, let's take that arrow away, between 0 and 8 in this region. And 1 is good because cube root of 1 is just 1, 8 minus 4, that's positive. Put a positive here. And finally, we can pick a value in this region here. And let's see, it might be good to pick something that has a nice cube root. I can pick any number, so why not 27? And then we would get 8/3 minus 4, which is going to come out to be negative. So we will take this number line analysis onto the next slide and then sketch a graph of this function. So finally, let's call up that number line analysis from the previous slide, and we're at a stage where we can sketch this graph. But first of all, let's interpret. So as we learned earlier in the video, f prime, whether it's positive, negative, d/e, or 0, gives us so much information about the behavior of the graph. So let's just summarize this. So f prime is negative up until 0, so we know that f is decreasing. Then it's positive, which means f is increasing, and negative, which means f is decreasing again. And we also know by the first derivative test that this must be a local min at x equals 0. In fact, if we take 0 and if we plug it into the function, we can also get the y coordinate while we're at it. And we also know here, because of the behavior of f prime on either side, that we have a local max. And that's at 8, comma, and if you plug 8 into the function, you'll get 19. So that's f of 8, the original function, remember, not the derivative. And so now we can put this all together. Now, we do know this time that at 0, 3, we have a minimum here, but we also know that the derivative is not defined. So don't do any nice smooth curve there. You've got to do something that suggests like a corner or a cusp that the derivative is undefined. And then at 8, we do 8, 19, we do know that we have a local max. And then from negative infinity to 0, yes, it's decreasing. And then it's increasing again, and then decreasing. Now, so there we are, very powerful. The first derivative is very powerful. The only problem is that it doesn't quite tell us in which way a function is decreasing. So the function, for all we know, up from negative infinity to 0, it could be decreasing like this. So we don't know if it's decreasing in that way, or maybe it's more like this. And in the next video, we will be looking at how the second derivative helps us to fully complete an analysis and sketch of the function.
And that brings us to the end of this lesson. I hope you found it helpful, and if you did, please do click like and/or subscribe to my YouTube channel, Ready to Derive. Thank you.